Hello all and welcome to this video where we look at the fundamental theorem of calculus and the definite integral. Now this is actually a really important video because we're going to connect that idea of the definite integral, which was something like this, which told us the signed area under a graph, which this is what this slide is a quick reminder of, and the indefinite integral. So the fundamental theory of calculus connects these two things. Where the indefinite integral, this gives us the antiderivative. So this actually gives us a function, and then this definite integral on the left, that gives us a number that tells us the signed area under a graph. So what is a signed area under the graph? Well, in this case, this is an example of finding the signed area where any area above the graph is considered positive and any graph below the axis is considered negative. So in this case, we're actually finding the definite integral between, in this case, it was -2 on the left. And we want to get in the habit, you won't always be given questions, and I'll show you a way to convert it, but you always want to write one of these signs working left to right, where at the bottom is the left and at the top you put your right number. So we're going from -2 at the left over to 2 at the right of x plus 1, and this working out just using area of triangles, we can see this top area is equal to 9 on 2. This area here at the left is half. So if you do 9 on 2, take away a half, because the area on top is positive, the area on the bottom is negative, so we take them away from each other to find the signed area. We get 8 on 2, which happens to be 4. Okay? And that's what this slide is just doing a quick reminder of. When we do this sign with numbers at the top and the bottom, what are called terminals, we need to get a number as the answer because we're getting a signed area. Quick thing to note, that is different from the total area. The total area would be doing the 9 on 2 plus a half, and we'll come back to that a little bit later, but it's a really gotcha thing. This symbol gives you signed, which considers above, positive, below, negative. So let's jump into it. How can we connect a definite integral with an indefinite integral? Well, the fundamental theorem of calculus tells us that. It just so happens, and it wasn't all of these symbols and all of this wasn't discovered all at once. We figured out how to anti-differentiate, came up with this idea of a definite integral being the area under a graph, and then all of a sudden people figured out that they are actually really closely connected. So the area under graph, that's what this is saying, is equal to g of b, so taking this top number substituting in, and then this bottom number substituting in to this function g, where g is the antiderivative of f. It's really elegant once you understand what this is saying. The area under any graph, f of x, is equal to substituting in the furthest right point into the antiderivative, taking away substituting in the furthest left point into the antiderivative. Another way you can sort of think of it is, no, I don't want to go into that because it's technically incorrect notation. Another way that we write this, because this g of b minus g of a can get a little confusing, is we generally actually write this, because g of x is equal to the antiderivative, we generally write it like this, where we put square brackets, and again we put the furthest left point down the bottom and the furthest right point up the top, and then you can substitute that in. So first you'll, I don't want to get too ahead of myself. Let's just take it that when you want to find the area under the curve between 2 points, you need to find the antiderivative, and then in the antiderivative you sub in the furthest right point, and then you sub in the furthest left point. And that will give you the area under the graph. It's really quite elegant, and becomes more obvious as we get into it. Okay. To think about this visually, there's another thing we can add in here, where the antiderivative of, say, just b of f of x is equal to the area from x equals 0 to x equals b. We could also say a up the top now. Normally it's down the bottom here, but f of x is equal to the area from x equals 0 to x equal b. But when we write it like this, we're saying, let's put some colors on this. So this is the area from x equal to 0, so that's all of that. This bit here is from 0 up to a, so this bit. So it's obvious that this bit here is technically equal to integral up to b of f of x, take away the integral up to a of f of x. And that will give us this area here. So instead of writing it out really long like this, we actually just stick the a down the bottom. So that's our left point. But yeah, so let's do an example. Okay, what is the area? And here, this is just a reminder of the fundamental theorem of calculus, this line here. Okay, let's look at this example 1. Evaluate the definite integral from 1 to 3 of x dx. What is this actually saying? This is asking, what is the area between x equals 1 and x equals 3 under y equals x? Okay? And again, it's a straight line, but we can work up to it. So using the fundamental theorem of calculus says, well, that area is equal to, find the antiderivative and substitute those two endpoints into it. So first off, and let's change this, this technically shouldn't be there. Okay, let's first off find the antiderivative. What is just the antiderivative of x? Well, the antiderivative of x turns out to be half x squared plus c by just adding 1 to the power and then dividing by the new power. That's the antiderivative. If we want to now find, actually I should leave those marks there because they shouldn't be there. Now, if I want to find what the area is between those 2 points, I need to substitute the 3 in, and then I also need to substitute the 1 in. And once I do that and simplify, I get 9 on 2 plus half, take away half minus c, making sure we put this second bit in brackets because that's this bit here. We're taking away the whole lot. And it turns out always c cancels. And then we got 9 on 2 take away half is 8 on 2 is equal to 4, which confirms what we had from the previous slide. So this is the long notation. First find the antiderivative, then substitute both points into it. The shorter notation to write is we can start straight away with the definite integral and then just write the antiderivative in square brackets. This is the antiderivative. Put in square brackets and we put the 3 and the 1. That's saying we need to substitute the 3 and the 1 into it. So we substitute the 3 into it, we substitute the 1 into it, simplify, and we get the same answer as 4. Okay. And I'm pretty much always going to do this way. There's nothing mathematically incorrect about it, it's just some notation that people developed that make it a little bit more efficient to do all your working out. So let's do some examples that might bring this all together. Okay. So we need to find the definite integral of between 1 and 2 of x squared dx. Well, I'm going to put square brackets, so let's put some little steps. What am I going to do? I'm going to put square brackets 2, I'm going to find the antiderivative. So the antiderivative of x squared, well, it's add 1 to the power and divide by the new power. And technically there's a plus c in here. Let's for now keep writing the plus c, but it's always going to disappear. And this is where people make the mistake, is because most of the time, the reason we teach all this antiderivative is to actually do these and the c's disappear. But then when you come to the exam and you're asked to just find an indefinite integral, you forget about the c and you lose a mark. And we're finding it between 1 and 2. So we put end points, we'll call it for now. Okay. And then step 4 is we're going to sub in endpoints. Okay, so we're now going to get this is equal to 2 to the 3 on 3 plus c, take away, because it needs to be take away between them, 1 to the 3 on 3 plus c, that is going to equal, that's 8 on 3 plus c, take away 1 on 3, take away c, bringing the negative in. That is going to equal 8, take a third, that's going to turn into 7 on 3. And that's our answer. That's the area under the curve x squared between 1 and 2. And that was x squared. That's a curved line. And that's just found it. Okay. Sometimes we're given numbers that aren't sort of written left to right. We can still substitute them in. We just got to be careful with our order that we're substituting the top number in first, then we're substituting in the bottom number second, and we're doing a subtraction between them. So this is equal to, add 1 to the power, divide by the power, plus c between 1 and 2. That's going to be equal to 1 to the cube on 3, take away 2 to the cube on 3, and I've dropped the c's because I know they're going to cancel. So we get 1/3 take away 8/3 is equal to negative 7 on 3. Okay. And here's something interesting, and we'll show you a rule in a minute that clarifies this. But if we have our numbers left to right, we got this answer. But if we reverse the numbers, if we write them right to left, we get the same answer but negative. And this is a really important rule that we'll remember, and will give you a sort of equation that gives it to you in fundamental form. But this is a thing just to remember. If you switch the order of the numbers, you'll get the same area, but it actually seems to gives it to you in a negative. Okay. This one here, when we have two terms that are separated by a plus, we can still apply our indefinite integral rules where we can split that up. So we can turn this into 0 to the 4 x to the half plus, and then we split the other term off in its own integral. And then we can work on them individually. So this is going to be equal to, add 1 to the power, so that's 3 on 2, divide by the new power, between 4 and 0, plus, and we do the same over here, add 1 to the power, so that turns into 5 on 2 on 5 on 2. Oh, and I forgot to carry the 4 and the 0. Between 4 and 0, so that is equal to 4 to the 3 on 2. Let's simplify. So that 3 on 2, instead we can put it out the front flipped. That's going to become times by x 4 to the 3 on 2. Plus, same over here, that's 2/5 of 4, because we put 0 in, 0 to anything power becomes 0, then divide by something is still 0. So substituting in the 0 just gives us 0, so we can ignore that. 4 to the 5 on 2. Now, I'll put it over here at the right. How can we change this 4 to the 3 on 2? Yep. Using our index laws, we can write this as 4 to the half to 3. So 4 to the half is square root of 4, which just is 2. cubed is 8, so that gives me 2/3 by 8, and we can do the same for the 4 to the 5 on 2. 4 to the 5 on 2 is the same as 4 to the half by 5, so that's equal to 2 to the 5, which 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So we're going to get plus 2/5 of 32. That's equal to 16 on 3 plus 64 on 5. And just to save our time, I'm not going to keep going on with simplifying fractions, but you get the idea. Rightio, so here are some of the rules that we've talked about. Let's start by explaining this one. This one's pretty simple. If your two endpoints are at the same spot, well then your area is clearly 0. Yeah. You're finding the area under the curve between x is 2 and x is 2, well, area is 0. Following on from our indefinite integral rule, we're looking at this third one here. If we have a scale factor out the front, in front of the function, we can bring it out the front of the integral. That's really handy. As we just talked about in that last worked example, if we have two terms separated, or two functions separated by a plus or minus, we can separate them out into their own individual definite integrals. And this last one here is the proper notation for that, where we discovered if we flip the order of the endpoints or the terminals, we're going to get the same answer. It's just going to be negative. And that's what this rule here is saying. We'll get the same area, but negative. Okay. With that, we generally want to try and work in left to right. Sometimes you'll be given information though right to left, sort of as this is given. We can flip it back to this by just whatever area we do find, we just change the sign of it. Now, last but not least, this first one. This first one, actually all of these will come up in the Year 12 exam, and a combination of these. There's always some questions in the multiple choice section around this at a minimum, and generally some short answer as well. But here, I want to find the area to A to B can be considered the same as the area from A to C and then C to B. So this is much easier explained using a picture. And we'll use this sort of line we have here. Let's say that is A, that is C, that is B. The area all the way along, which we'll say is this, from A to B, is the same as the area from A to C, that bit there, and the area from C to B. It's just breaking it down into smaller parts. Pretty obvious. But again, they like to give questions around, maybe giving you some information that the area of this section here is 5, the area of the whole way along is 15. What's the area here? Well, if the left bit is 5, the whole thing's 15, take away the 5, that means this section here is 10. They love to give questions like that. So here's an example of it, based off some Year 12 exam questions. We're up to 20 minutes, so this video is going to go a bit longer. Sorry, team. We still got a bit to get through. Right, given that the area between 1 to 5, so we've just done a little diagram. We don't know what the line looks like. We're just told it's f of x, so some line, but we're told the area between 1 and 5 is 16. And we're also told the area between 2 to 5, so we're going now 2 to 5, this area here is 12. Find the area between 1 and 2. Well, again, pretty obvious. If the whole area is 16, this area here is 12, that must mean this section here is 4. So it's just trying to think logically, drawing little sketches. Doesn't matter what line you draw, but you can always just draw some wavy line, put lines down, put numbers you're given. So you might be at, and fill some numbers in the box. But let's have a couple goes at it. So here we go. We're told, and one thing to check is we're told numbers are working left to right, so that's going to make life a lot easier. We don't have to do any changes yet. So between, let's fix that. I'm going to put a central diagram here. Okay, let's put black axes. Left function, let's put a line in. Some squiggly line, some function. We have some function f of x. We don't know what it is, but we do know the area between -4 and -2. -4, -2. That area is 5. Let's fix my scale again. So that area in there is 5. We're also told from 1 to 4 is -2, so let's maybe go red for that. From 1 to 4, so that's 1 to 4. We're told that area there is -2. Now my picture doesn't match. To be negative, it would have to be under the axis, but this is fine, just for getting an idea. And then we're told the whole way. So from -4 to 4, so let's put some blue over the top. That whole way, that area there is 6. So if we can visualize that, now we can figure some things out. We need to find the area from -2 to 1. Well, that's going to be equal to this section in here, -2 to 1. Well, we were told the whole way along is 6. Let's take off this left hand, the green bit. So 6, take away the left, is going to be 5. And then we're also going to take away the right, which was -2. That's going to equal to 3. We need to find the area from -2 to 4. So we're now trying to find from there to there. Well, we just found that -2 to 1 is 3. So from -2 to 1 is equal to 3. Let's take away, and we also already know that from 1 to 4 is equal to -2. So the total is going to be equal to 3 plus -2 is equal to 1. Okie dokie. Right, now we're trying to find from -4 to -2, -4 to -2, but of 5 f of x. Well, this is where we can use our scale factor rule, just bring the 5 outside. So that would be equal to, from -4 to -2, bring the 5 outside of f of x dx. So that is equal to, well, between -4 and -2, we were told, that's the green one, that's 5. So it's going to be equal to 5 times the 5 is 25. From -4 to 4. Okay, so now we need to just notice that we aren't left to right. The order is switched compared to up here. So that would be equal to, we want to switch the order back to something we know. So we want to change this to 4 at the top and -4, because that's what we're given up here. We switch the order, we have to put a negative sign in front of it. And that will give us negative, and we're told the area is 6. So we can put that in. Okay, last but not least, we want to find the area from 1 to 4 of f of x plus 2. So if we think about what this is, plus 2, that's sort of like a k, that's our k value, because we've just got the function and we've got plus 2 added on the end of it. So our line is exactly the same, but it's moved up 2. Well, how can we work with this? Well, that's a function, this is a function separated by plus sign, so we can separate that out. So that becomes a 1, 4 of f of x dx plus the integral of 2 between 1 and 4 regards to x. 1 to 4 of f of x, we have already been told it's -2, so that gets us -2, and then we just need to actually figure this out. So the antiderivative of 2 will be 2x, and we're going between 1 and 4, so that's going to be equal to -2 plus, substitute the 4 in as 8, substitute the 1 in as 2. When we substitute the second number, we have to subtract it, and we're going to get -2 plus 8 take 2, the area will be 4. Rightio. How are we going? We've got a couple more slides. I apologise for the length, but this is pretty core to the rest of the topic. Right. We can also think in terms of transformation or applying those these rules. These rules are really handy to break problems down into information that we've already given. So let's have a go at this. We know between 0 and 2 of g of x dx is equal to 5. Then what is, notice the orders change, 4 minus 3 gx. This one is nice that you don't actually have to think in terms of transformations. We can apply all of those antiderivative laws to make this into a problem that's a lot easier. So first off, we can split at the minus. So we've got 2, 0, 4 minus 0, 2, 3 g of x. That is equal to, and I'll do the antiderivatives at the end. 4 minus, same with this 3, we can bring it out the front. That's a scale factor, 2, 0, g of x is equal to the antiderivative of 0, 4. Let's just put 3, that 4 needs to stay there. G of x. Now I want to change the order back to what I have information about. So that's going to be 0 to 2, which is what I've given. So since I've changed it to 0 to 2, I need to change the sign in front, so that's going to become a positive. And now the rest of it's pretty easy, so I'm going to find the antiderivative of 4, which would be 4x between 4 to 0 plus 3 by, and we're told between 0 and 2 g of x is equal to 5. Is equal to, substitute in the 0, substitute in the 4, we get 16. To subtract the second one, plus 15, that is going to equal to -16 plus negative. What have I done wrong? I did this before. Not the right answer. I'm pretty sure it should be 7 or -7. Where have I gone wrong? Oh, why did I write a 4 down the bottom? That's a 2. There we go. 2, 8. There we go. 7. Answer is E. Right. Now, this though is where we need to start thinking about what are the transformations applied to the function, and what would that do to the area, and use a bit of conceptualization. First off, where there is the plus, we can separate that out. So we can write this as 2 integral, let's put 2 in 5a 0, you're going to get fx on 5 plus integral between 0 and 5a of 3. And the 2's out the front of all of that. So first off, we can split it. Now, this we can do, and we'll just end up substituting, but what we really care about is this. How can we deal with this x divided by 5? Right. Okay, so if we had f of x, and we've now got f of x divided by 5, think of transformations with using inspection. We have replaced x with x on 5. So what does that mean for the function? And then think of what does it mean for the shape? Well, that means we have dilated by 5 from the y-axis. Okay. So if we think of what our original shape is, hold on, replace with x on 5, yeah, dilated 5 from the y-axis. Okay, if we think of what our original shape may be, again some squiggly line, and we're going between, in this case we're told our original shape is between 0 and A, so that's A there. We are now going, that shape has been changed, so let's actually give some sense to scale. That line has been dilated up by 5. So if our line has been moved up by 5, our area is essentially times by 5 as well. Cool. So our area is increased by 5. This is, again, takes a bit of a nuanced look, is, okay, then how do we resolve this 5a instead of the a over here? Well, if I put 5a into this where x is divided by 5, that is essentially the same as 5a divided by 5 is a. So my function area is increased by 5, but I'm still technically finding the area, or simplified, I can think of, I'm still finding the area between 0 and a, but the area is increased by 5 times. So I'm going to get 2 times by 5 by that, so I get 5a plus 3x between 0 and 5a is equal to 2 by 5a plus 15a take away 0. So it's 0 in. So we get 2 by 20a. So we get 40a. And there's our answer. I fully get there's a lot in there. But yeah, you have to, again, drawing little sketches like this, think about, okay, I'm told some information about a basic function, this area in here, what are my transformations doing to that line, and then what are they doing to that area? So they're stretching it up, maybe it's doubling the area, or in this case it increased the area by 5. What happens if I completely drew that wrong? Oh my god, I've just realized. That makes much more sense. I was trying to explain 5a. My apologies. We're dilating by 5 from the y-axis. We've stretched this area out by 5. Okay, so my area is increased by 5, and I'm now at 5a. So this point originally, and this shape has been stretched out. So this line, if I drew it somewhat to scale, has been stretched out by 5, and that makes more sense with the substituting in 5a. It's this whole area increased by 5 times. My apologies. Right, let's have a go. And we'll make this the last slide. If between 2 and 6 f of x dx, the integral of that is 7. So again, let's just draw a little random line between 2 and 6. The area is 7. That's what we're told. Find half of between -1 and -3 of 3 minus f of -2x dx. Ooh, that's a lot. That doesn't look nice. But again, we've got a subtraction in there, so we can start to simplify it out. So that is going to be equal to half of -1 and 3 of 3 minus the integral between -1. -3, -1 of f of -2x dx. There we go. Right. Okay. This first bit, oh, and I forgot to close the brackets. This bit here is as simple as just finding the antiderivative and substituting the points in, but this is a little bit more complex. Again, we need to think of what are the transformations that have been applied to f of x to now get this f of -2x. Well, I could write that. Let's think of replacements. First off, I could replace x with -x. So that is reflecting about the y-axis. So that's taken this between 2 and 6, and that has now changed it and reflected about that, and we've now got the function that looks like this, but we still know, if we flip that, we still know between -2 and -6 now, this area must be 7. The function is exactly the same, it's just been flipped over, but this area must be 7, between -6 going towards -2. So that's getting the negative inside. What about the 2? Well, if you remember from inspection, we're actually, when we're dilating, we need to be replacing with like x divided by something. So to get the 2x, we actually need to replace x with x on half. And if we simplify that, we get 2x. So what does x on half mean? That means we dilate by half from the y-axis. Okay, so what does that now mean for the shape of our graph? Well, that whole graph has been compressed in by half towards the y-axis. So we've now got, we think of our area, we're now between -1 and -3, we've been squished in by half. So that means also, if everything's been squished by half, my area in this zone, I can reason that that's now half of 7. So that's just some logical reasoning, starting with, okay, I know this about this area. If I flip it over, well, the area is still the same. It's still 7. If I then dilate and squish it in towards the y-axis, well, if everything's halved, then my area must be halved. How can I use this? Well, I now know that this area in here is 7 on 2. How can I get this written the right way, or that represents that? And it turns out we've already got it written. You just want to make sure, and I did a check on this before, if the information about our original area is written left to right, even once we've done all these reflections, you need to make sure it's also asking to find the area written left to right. In this case it is, which is really quite nice, so we can just take away, we can straight away say that the area is 7 on 2. If for some reason this was written as -1 to -3, you actually need to flip it to match the order, going left to right as this one was. But we can say that that is equal to half bracket, this is going to be 3x, -1 and -3 minus, and we just proved doing these transformations that between -3 and -1, which we have down here, f of -2x, which we've got because we dilated it and reflected it, that area needs to be 7 on 2, so we can just put 7 on 2 straight in. You get half by, put -1 in first, so we get -3, take away, put -3 in, -9, minus 7 on 2, you get half by 6 minus 7 on 2 equal to half by 12 on 2, take 7 on 2 is equal to half by 5 on 2 is equal to 5 on 4. And there's your answer. So there's a lot in that. There's a lot in that. These are the exact same things, but when you're actually given the actual equation. And again, using reasoning, thinking of what has happened to the graph. Well, it's been moved up by +2. So if we know the area of this and this whole thing's moved up +2, we now also have this stuck on the bottom of it. And that's coming up like that. Well, what's the area in here, in this new square? That's pretty obvious that that's just going to be 2 times 1 because it's just a rectangle. So it's going to be 2 plus the original area. E take 1, so that's going to be equal to 1 plus E. What about 3 minus e to the x? So minus out the front. So we can write that as 0 to 1 of 3. So we're now, what that is essentially saying is, what's that area in there? Minus 0 to 1 of e to the x. So the area between 0 to 1 under 3 is just obviously 3 minus, we're told up here, e minus 1, put in brackets just to avoid sign errors, is equal to 2 minus e. And lastly, we want to know now the area between 2 and 3 of e to the x minus 2. Well, we've replaced here, if we look, we've replaced x with x minus 2, so h is equal to 2. It's just been moved across 2 places. It's now sitting over here, and it's doing the same thing. It's the area between 2 and 3. So this actually happens to be the exact same thing. E minus 1. Okay, wow, really long video. There's a lot in it. The takeaways. Something like this is trying to find the, oh, that's 1 and, oh, I didn't read that properly. That's a trick question. If this was 0 to 1, what we did was right. Between 1 and 1, the actual answer is 0. My apologies, I just noticed that. Yes, trick question. I forgot about that. But if it was 0 to 1, we'll leave this here as valid reasoning. Right, but what I was saying, if something is written like this, we are finding the area under this curve between the points x equals 0 and x equals 1. We can find that by finding the antiderivative of this and substituting these two numbers into it and finding the difference between them. That's what the fundamental theorem of calculus says. That's what this says. Find the antiderivative, which is called g, substitute b into it, and then substitute a into it, find the difference between them, and that's always going to give you the area. That's pretty darn handy. What would be nice to take away that you're at least comfortable with is doing these, just finding the numbers, and if we're not so good at, especially this stuff with dilations, transformations, and using given information, that's okay for now, but it would be at least nice if you come into class being pretty happy with this idea and being able to do that. At the end of these slides, there are some practice problems for you to have a go at. Some easier, some harder. See you in class tomorrow, where I'll let you have a go at those practice problems and we can talk more about this because I'm sure you're going to have questions. Thanks, and see you then.